In today's lesson, we will be continuing our discussion of normal distributions, specifically finding the inverse value of a normal distribution, meaning if we're given the probability ahead of time, can we find the actual data that would be needed to find that percentage or probability. We'll be doing this using mostly technology, but a little bit of graph drawing as well. So what happens when we have a percentage or probability but don't know the data value? For example, suppose we have a population of adult snails where the length of a snail shell, x, is normally distributed with a mean of 23.6 and a standard deviation of 3.1. What is the shell length that is longer than 95% of the data? Well, to start with, I'm going to do a quick little sketch of a normal distribution. Again, we have our bell curve, should be symmetrical, and we know that we would have the mean that's right down here in the middle. We represent that with mu, and in this case, our mean is 23.6 millimeters, and each standard deviation is 3.1 millimeters away. And we are trying to find the length of a shell that is longer than 95% of the data. Well, one standard deviation would get me an additional 34%, and we continue on here. We should have about 95% of the data somewhere around here where I drew that second line. And so I want this shell, this unknown value, which I'm going to call k here, should be bigger than all the other values that I'm highlighting here. So that would be my shading. K is greater than all of those other values there to the left. And so the question is, how can we actually find that value? And the idea is that we'd use inverse norm. Inverse norm measures percentages from the left of the graph. And so if I put in 95% into my inverse norm calculation, it would, move from the left of the graph and find the value that is greater than 95% of all the data, as I've labeled here, which is k. And so let's give that a shot. Pull out my calculator here. And so I go to my my distribution menu on the calculator. So second distribution, which is the vars key. I don't want normal PDF or normal CDF like we used last class. We're going to use the inverse norm, which is the third option here on my distribution menu. I hit enter. What it is looking for now is first my percentage. Calculators don't want them written as percentages. They want an actual decimal. So we put in 0.95, comma, then we put in our mean, which is 23.6, and last but not least, we put in 3.1 as our standard deviation. So we know that this should be about 2 standard deviations away, 23.6. Each standard deviation is just a little over 3. If we had 2 of those, it'd be a little over 6. So we should be around 30, just a little bit less than that, maybe 29, somewhere in that family. And I hit enter, and voila, 28.7. So very close to my estimate there. So again, going back to the original question, it said, snail population, what shell length is longer than 95% of the data? So if I was a snail and my shell was 28.7 millimeters, I would have a bigger shell than 95% of all the other snails. And that's what that says. All right. So that's the main idea of today's lesson, using that inverse norm. The thing to remember, though, is once again, the calculator, you put a percentage in. You put in 50%. You put in 95% like we just did. You put in 15%. It doesn't matter. It will always measure from the left side of the graph, meaning that you can see this shaded area here and the k that's written down here. If we put in 50%, let's say, into our graph, it would measure 50% of the left, and your k would be right there in the middle. If you did, 95% like we did, well, then it's going to go 95% of the data all the way over to that k value. Now, if you put in something like 15%, it's going to be way over here on the left. Somewhere like here might be my new k value if I put in 15%. Only covers 15% of the data from the left. So what happens when we want to have data on the right? Well, like that last problem, for example, if instead of wanting to know that I was bigger than 95% of all the shells, what if I wanted to be smaller than 95% of all the other shells? Then my K value would be over here, and my shading would be here. So you have 95% of all the data, and my K value is smaller than 95% of all the other data. If you're smaller than 95% of the data, though, then what percent are you bigger than? And that is 5%. And that's where this idea comes in. So anytime we're talking about our data and we want it to be less than, or the probability that we're less than a certain value, then we are using this 1 minus p. And we'll look at an example of that coming up right now. A history professor determines that 80% of this year's history candidates should pass the final examination. The examination results are expected to be normally distributed with a mean of 62 and a standard deviation of 13. Find the lowest score necessary to pass the examination. So if we listed all of our scores on a number line, and that was normally distributed, again, we'd have our mean score right here in the middle, and we'd expect that to be 62, standard deviation of 13. We want our the score that the professor determines so that 80% of the students pass. Well, think to yourselves, are passing scores high scores, or are they generally the lower scores? They're generally the higher ones. So if 80% of students are passing, that means certainly the top half is already passing, everybody greater than that. And then another 30% is also passing. So somewhere around here, meaning this is my K value. But you'll notice that I just shaded to the right because the passing scores are the higher scores. So I've shaded everything greater than K, and I want this whole area to represent 80% of my data. Well, if to the right of K is 80%, what percent would be less than K? Because remember, the calculator always looks what you put. If I put in 80%, it would actually find 80% from the left, and it would give me a K value right there, which is not what I want. So I need to put in the complement of that. Well, 80% we can write as 0.8, and so 1 minus 0.8 equals 0.2. So that means that 20% of my data is what I want to actually put into the calculator to find the score. So 20% of my data would be less than this value of K. So we're essentially finding the failing students here. So pull out my calculator again. Inverse norm once again. And really, if you press second enter, that always does the same keystroke you just did. It repeats it. So you can just change values here if you don't want to go through the menu. So we'd have 0.80 for our 80%. And then our standard deviation was 62, comma, and our mean was 62, and our standard deviation was 13. And I had some extra stuff there, which I will delete. So percentage, 80%, 62, and 13. But we said that we couldn't use the 80% because that would measure from the left. We needed to use the complement of it, so I should put in 0.20. So 0.20% to the left of my value, 62 is my mean, 13 my standard deviation, and that means the score on the test should be 51. If we go back to the picture that I had sketched earlier, again, we said that if this is the mean, my K value should be somewhere over here, so that I have 80% of the data to the right of it. And if the mean is 62, our K value certainly should be less than 62, and we do have a value that is less than 62, 51.1. One more example, and then we'll call it a day. Shorter video than last time for sure. The life of a xenon battery has a normal distribution. The mean is 33.2 weeks, and the standard deviation is 2.8 weeks. If a battery is selected, find the probability that it will last at least 35 weeks. So let's start with that one. So all right, mild technical difficulties, but I think we got it worked out. So we want to find the probability that it's at least 35 weeks. So you can think of this data having your x-axis. Your data is how long it takes before the battery fails. And we have a mean of 33.2 weeks, which would be right here in the middle, 33.2 weeks. Now, some batteries will fail earlier, and they will happen over here. Some batteries will last a little bit longer, and they'll fail over there. But again, the average is 33.2 weeks with a standard deviation of 2.8. So we're asked now to find the probability that it will last at least 35 weeks. Well, what have they given us? They've given us actual data, an actual X value. So is this inverse norm, or is this the regular norm that we did in the past? We want at least 35 weeks. We could rewrite that to the probability that our data X is at least, meaning greater than or equal to 35. So we're going to use our normal distribution CDF program on our calculator. And again, we want our data to be greater than or equal to 35. So our lowest piece of data is going to be 35. Our highest is infinite. And again, if we drew that on the graph, greater than or equal to 35, it'd be about here. And so we're finding this value here. It should be a little less than 50%, maybe, 40 and change, something around there. So let's try it on the calculator. We go to second distribution, choice 2 for our normal CDF. And we want to have our lowest value first. Our lowest value is the 35 weeks. Our highest value is the positive infinity, which would be E99. Again, we get the E from second comma. And then we do our mean, which is 33.2, and our standard deviation, which is 2.8. Close our parentheses. And, less than I expected. Making sure I did that right. Yep, 35, 33.2, 2.8. Looks good. Okay. So 26%, 26.0% would be our answer on that one. Find the maximum number of weeks for which the manufacturer can expect that not more than 8% of the batteries will fail. I think we need to draw a picture here on this one. So once again, we've got our weeks. Let me do a fresh picture here. And our curve, our mean is right here at 33.2. And we want to expect to have no more than 8% of our batteries will fail. Well, our first batteries start to fail way down here, so 8% should be somewhere around here. This is our K value, where it would be only 8% of our batteries would have failed at this point, no more than that. And so we're going to do our shading. Is it to the left or the right? We need to ask ourselves. Again, the calculator likes to the left, and that's how we've got it shaded. So our K value would be greater than 8%, not any more than that. And so we're going to go to distribution, inverse norm. We put in our percentage, which is 8%, which you write as a decimal is 0.08. We have to move the decimal twice. And then we put in our values of the mean, 33.2. And our standard deviation, which I believe was 2.8. Again, only bigger than 8%, so we're looking at less than 2 standard deviations, but more than 1. And so we should be somewhere right around 30 on this one. Yep, 29.3. And that is our value for the maximum number of weeks where we'd expect only 8% or less to have failed. All right, so that's inverse normal distribution. So our homework will be on page 645, number 3, and number 5 through 9.